Hello everyone, this is Junaid here from Edureka and I welcome you all to this session in which I'm going to talk about long short-term memory networks. So without any further delay, let's take a look at today's agenda. We'll start this session by understanding what is natural language processing and why do we even need it. Then we shall discuss both machine learning and deep learning approaches to process our textual data. Moving ahead, I'll be speaking about recurrent neural network and long short-term memory. Finally, we'll end this session by discussing the use cases of LSTM and few of the real-world applications. Alright, now to start off, let us now understand what is natural language processing and why do we even need it. You see, natural language refers to the speech analysis in both audible data as well as a text document. NLP system can capture meaning from an input such as sentences, paragraph, pages, and give out a desired output based on our application. So why do we need NLP? You see, natural language processing helps computer communicate with humans in their own language and scale other language-related tasks. For example, NLP makes it possible for computers to read text, hear speeches, interpret it, measure the sentiment, and then determine which part of it are important. Today's machines can analyze more language-based data than humans, that too with consistency, accuracy, and in an unbiased manner. More or less, we all know that there is a staggering amount of unstructured data that is generated every day, be it from a medical record or to a social media. Automating NLP tasks will critically be helpful in future for analyzing text and speech data efficiently. So moving ahead, let us now see the ways we can process our textual data. We can process our textual data in one of two ways. One is a machine learning way and other one is a deep learning method. In machine learning, we can make use of algorithms such as bag of words, TF-IDF to classify and predict the desired output. But the drawback of this is that these machine learning algorithms do not consider the context of the word or a sequence. Here, the way it works is based on number of times the word is repeating, a probability is derived out of it, and then performs a classification task. This is the reason why we have deep learning model for NLP tasks. Speaking about deep learning model, we have something like Recurrent Neural Network, LSTM, Transformer Network, Google's BERT algorithm, and many more. This deep learning model learns the pattern of a word or a sequence and then tries to predict the desired outcome of the task. We can perform NLP using deep learning in one of two ways. One by pre-trained models such as Google's Word2Vec or global vector models. And the other way is to train our own model. If we are trying to train our own model, it would require a very huge amount of data and also compute power to support it. In most of the cases, we will be using pre-trained models. Moving ahead, let us now discuss recurrent neural networks. As I mentioned earlier, the bag of word or TF-IDF model for processing our text is very inefficient. As I mentioned earlier, the bag of word or TF-IDF model that was used in machine learning to process our textual data is very inefficient, as it takes one word at a time and also the context of the word in which it is being spoken about is totally ignored. Although this would give us some prediction, but we can expect a lot of loss. This is why we use RNN model or recurrent neural network. Here, it requires a sequential data. Now you might be wondering, what does this sequential data mean, right? In simple words, sequential data is dependent on the past values. What I'm trying to say here is that we can read our document, right? We can read our document or English documents only from left to right side. Or take example of stock price prediction. We cannot randomly place the dates, right? If you have to make a prediction for next 2-3 months, we'll obviously refer to the data that was previously recorded. So this is what a sequential data means. So what makes RNN capable of handling sequential data? Well, you see, RNN model makes use of something called a state. This is nothing but a temporary memory that stores the previous data. As you can see here in an image, this is the general architecture of a recurrent neural network. So let me now move to my canvas and show you how recurrent neural network works and what are its internal workings. Alright. So as we have seen in an image, right, back in our slide, you saw that, recurrent neural network have something called as states, and then we also had some boxes, right? So what does those boxes represents? So let me quickly draw over here and show you what does this box represents. So if you remember, right, it goes something like we have a box here, okay, and then we also had another box, and then let's consider like 2 more boxes, that would be sufficient, okay. And then the way we provide input for our recurrent neural network is over here. Okay. Now, based on our application, we can demand our recurrent neural network to provide output in either one of the 3 ways. It can either be like we can have multiple inputs, as you can see here, or we can have single input and multiple outputs, or the other way around is we can have single input and single output. So here what we'll consider is we are using multiple inputs and also we have multiple outputs. Okay, so now let us see, as this is a supervised learning model, right? Obviously it will have some kind of input and then it will also have labels to clarify the data. So let's take something like, if this is our X data, right? So if this is the X data, so let's take this as a list, and then over here we'll have data which would represent something like X1, then we'll have X2, then we'll have X3, and then so on, and we'll have something like Xn. Okay, so what does this X over here represents? See, here let's take an example that Uri, which was a movie, is a good movie. We can have a couple more X's and we'll just put here as good movie. Okay, so this is nothing but the inputs, each of these words. Now, what our model over here does, let's take an example that we are trying to find name entity prediction, which stands for NER, right? So what this name entity prediction does is, trains the model in such a manner that it finds a pattern. So as you can see here, this is Uri, right? Uri, it's something like a name, right? So this goes as 1, and is not a name, so this would be 0. Good, this is also not a name, and movie is also not a name. So the output over here would be something like 1000. All right, so now let's see what are the inputs and how it would look like. So first off, we have inputs. So if this is our X data, so we'll have input something like Xi. This would be in lowercase. Okay, so this would be X1, then we'll have X2, we'll have X3, and then we'll have X4. Similarly, the Y, the output over here would be something like, we'll give it Y hat of 1, Y hat of 2, Y hat of 3. At the same time, we'll also have Y hat of 4. Now, if you're wondering what does this Y hat represents, Y hat over here is nothing but predicted values. And Y is nothing but, the labeled value or trained values. And now, as we all know that the main thing or the main feature behind recurrent neural network is nothing but the states. And the way the states are represented is by using the state vector, or it can also be called as context vector. So the state vector over here starts with A. Let me give it as a different color here. Let me give it as blue. So here we'll have A, and this would be 0. Okay. And now this A would be passed down to this. Okay. So this would be A of 1, and over here we'll have A of 2, A of 3, and then finally A of 4. I'm pretty sure you might be wondering what does this A contains, right? So over here, as I have mentioned, let me take this very example. So here Uri is good movie. Okay. And so what this A1 will contain? A1 will contain Uri. See, if we take the normal algorithm, what's going to happen is it will just consider only this one particular block. Okay. If this was just a normal algorithm or something which is used in the olden days, it will just consider this particular block and it won't be considering the previous values. So this previous value is being stored over here in the form of a memory. So now A1 will contain Uri, and what A2 will contain over here. So A2 will be having something like Uri is. And similarly, as it goes through here, it will collect each and every word. And finally, A4 will be complete context vector. So it will have the entire sentence, Uri is a good movie. Okay, I hope you understood what does this A signifies over here. Let me quickly erase all of these. Okay, so the another important part which goes over here in any machine learning or deep learning model is nothing but the weights. So let's consider that we have weights, which is nothing but W, or let's take it as U. Let me give another color here, U, V, and W. In this RNN model, right, what we're going to do is we're going to have a single, or we'll have just only one weights, right? So the U weight is same for all of these inputs here. V weight over here is same for all the outputs. The weight W is same for all our state metrics. Okay, so this is how the weights are determined. So now to get a better understanding of what's happening over here and to derive a mathematical equation for feed-forward network, let's take a single block over here. And let's see how this internal working of this is working, okay? So over here we'll have a box, okay? And this will be our input. So let's give our input as x of t, because this is a generalized model, right? And now what we're going to do over here is this would be a of t minus 1. That's because a of t will be present over here. And now if we have an output which is present over here, and this would be nothing but y hat of t. All right. So as I mentioned earlier that we will be having weights. So the weights over here is nothing but U, V and W. So what's happening over here? Okay, so first off, there will be a matrix multiplication between these two values. Okay, there will be a matrix multiplication between these two values. And once they are done, we'll add these two values and then give a activation function to it. Okay, and the activation function that would be used over here is tan h. So if I have to put it in an equation form over here, so the product of these two, x of t times, or it would be a dot product of u, okay, and the sum of these two, so it will be t minus 1 times w. And now what we're going to do is we're going to pass an activation function, which is nothing but tan h over here. So let's just give a small dotted notation over here. So whatever the output which comes, it will be performing an addition of these two and also give an activation function, which will represent here by f. All right. So this is how we get an activation function over here. So what does this value signifies this? This is nothing but this output over here, a of t. So I hope you understand what is a of t. A of t is this value. Okay, let me quickly highlight that for you. So a of t is this value. Okay, so a of t is represented over here. And the way we get this is by this particular equation. Now, what about the value for y hat of t, or the prediction of y of t? So for y of t, it's going to be something like this. So y hat of t, this would be nothing but we have to multiply this particular a of t with this matrix over here. Okay, or the weights I can say. So it's going to be nothing but a of t times the weight matrix, that is v. And then we have to pass activation function. Usually the activation function that is going to be used over here is softmax or sigmoid. It totally depends upon what kind of output you are expecting. All right, and this is how it works. And now an important thing that I would like to mention over here is that we also have to add something called as bias. So it will be b over here. I'll just represent this by a different color. So this is an equation for our recurrent neural network in a mathematical form. So now what's going to happen is, in order to find a loss, right, we have to subtract whatever value we have predicted with the given value. So the predicted value over here, let's say this is as capital Y. Okay, and we also have been given the trained value. So this would be looking something like this. So we'll obviously have the trained values. Let's just give a random output, but there will be 4. So it'll be 0, 1, 0, 1. Okay, so this is nothing but the trained values. And now we'll have the other, this is nothing but the given label data. So this would be correct values. So 1, 0, 0, 1. As this is a supervised learning, so we obviously will be given this label data over here. So now what this will do is this will subtract each of these values and calculate a loss. So how do we calculate a loss, right? Okay, so as you can see here, if I give this L, like, let me change the color here. So if I say L is loss, so this would be nothing but y hat of first value minus the actual value. Okay, so this is nothing but the predicted value, and this is nothing but the given value. So if I try to find out the loss of this, then what this would look like is, this is just for the one value, right? So if I have to do it for all the values, then it would be the summation. So it would be nothing but loss is equal to summation I, which ranges from 1 to n, right? And then we'll have loss and then theta I. Okay, so this Li over here represents these values. Okay, so this is just for one. So if you want me to explain you this in detail, so over here we have y1, y2, y3 and y4. How this would look like is something, so this would be for 1 plus y hat of 2 minus actual value of y of 2, then summation predicted value of y3 minus the actual value of y3, and then it'll be predicted value of y4 minus the actual value of y4. And when I perform addition over here, or when I perform summation, I can generalize this equation into this form. But we are not yet done over here. As you can see, we have something called as theta values. So what does this theta values represents? You see, the main agenda behind finding a loss is to increase our accuracy, right? So if I say this is my gradient descent and this is the lowest global minima, right? So my agenda over here is to reach this global minima. So now, in order for me to do this, in order to increase my accuracy, I have to obviously change my values. So how do I do that? How do I increase an accuracy? It's obviously by these weights. Okay, it's by this W, U, and V. So W, U, and V are nothing but the weights. So what this theta over here represents, let me quickly erase this. Okay, so what this theta over here represents is nothing but the values of W, U, and V. So now what we're going to do is we are going to have a partial derivative of the loss with respect to u, and then we'll have a partial derivative of loss with respect to v, and then we'll also have partial derivative of loss with respect to w. These are nothing but weights, and we are trying to train the weights. This is done in order to increase our accuracy. Okay, and the way these models get trained is with the help of backpropagation, and the way the backpropagation works over here is by partial derivative. So what I'm trying to say here is, as if I get my weights over here, so let me just take another color. So this v, we know that it is totally dependent upon this value over here. This won't be v, this would be w. Okay, so this w value will be totally dependent on the previous one, and this value will be dependent on this one, and this value will be dependent on this one, and this one would be finally dependent on this. So this is in order to move from here to here to here and then to here, we'll use something called as partial derivatives, right? So that's how we update our old weights. All right. And another important concept that make neural network or recurrent neural network very important is nothing but embedding layer. So let me quickly draw a boundary over here. Okay. So embedding layer. All right. So what does this embedding layer signifies? Okay. So if I take a convention way, right? So like, let's say that, our x, or, our input over here, this is nothing but x over here, right? So what is the dimension or the shape of this x? The shape of this x is nothing but 1, 4, right? 1, 4. Similarly, it's 1, 4 here, 1, 4, and 1, 4. But this is not usually the case when you're working with real world examples. When you're working with real world examples, we won't be having 4 different words, right? We'll obviously have lakhs of values. So for example, let's say we have x, and the shape of this x is something like, we have 10,000 values. Okay, so now if I try to feed this 10,000 values into my network over here, obviously I would be using batch propagation. So it would take a lot of time, right? Because it's 10,000 values after all. So in order to overcome this, what we're going to do is we're going to reduce the size of this. Okay, so basically what word embedding layer does is think that we have a matrix. This is our input layer, right? Or input word. So we call this as sparse matrix. This is nothing but, an individual value, that's xi or x1, x2, x3. Let's, for generalization, we'll give here as xi. And the shape of this is nothing but 1, v. V here represents the n number of dimensions. And 1 is because it's just going to be one word, right? So it's going to be 1. So if I consider with respect to this is 1 and this is v. Okay. So now what will happen is, if v is 10,000 or pretty great, it obviously we won't have much, we are going to lose a lot of time on computation and also take huge compute power. So what we'll do is I'll multiply this with an embedding layer. And what this embedding matrix does is, it is basically a set of features. So this is something, this is a black box model. And all this would do is this would attract a couple of features. If you want me to give you a better analogy of what this is, and if you want me to compare this with respect to a CNN, which is nothing but another great algorithm for image processing using deep learning, right? Over there, we are going to use something called as filters or kernels. So each of those filters or kernels is responsible for extracting one specific feature, right? So this is what embedding layer does. And what this would do, for example, now let's say that the size of embedding layer is v, k. K is something that we provide an input over here. So now what this would happen is, this would give us a new matrix or embedded matrix whose size would be 1, k. I'm pretty sure you didn't understand this because over here I'm using, these letters. So in order to make you better understand this, what I'm going to do is, let me take a matrix over here. Okay, let me take something like, because this would be in an embedded form, right? This would be a sparse matrix. So it will be like 0, 0, 0, 0, 0, 1, then we'll have 0, 0, and so on. Okay, so now what this would do is, we'll also create a matrix over here. The size of this would be something similar to that of v. This is nothing but 1, v, and over here it would be k. So the matrix shape over here would be v, k, right? To give you a better analogy, let me also draw a couple of boxes here. So this is the matrix, and this is the matrix over here again. So now what will happen over here is, when I try to perform this matrix multiplication, right? What this would do, as everything is 0 and only one value is true. So let's say this is the one value, right? And this would be going across, from left to right, and this would be from top to bottom. Only one part over here would be marked, and rest everything would be 0. Therefore, reducing the dimension, let me give some random values like 0.5, 1.8, 0.5, just some random values. So now this would obviously reduce the size of 1, k. So what I'm trying to say here is, now for example, say that I have a size over here as 1 comma 10,000, okay, which is a very huge matrix. And the shape of this, let's say that it's 10,000 comma 200. When I perform this embedding, right, word embedding, the shape of the new matrix would be nothing but 1 comma 200. If I compare this part over here to the embedding whatever we have received over here, so let me just give a quick brief. So this is our embedded layer. So this is really 1 comma 200. So you will see that we have decreased the dimensions by a drastic amount. Okay, so this is 10,000 and this is only 200. And this would be very efficient when we are trying to feed this to our recurrent neural network. And let me quickly show you how this would go. So first let me draw our architecture. Let's take this blocks like this. And then we'll have an output over here. Okay, so this would be our inputs, right? So let me give something like this. So initially we used to provide X values over here, right? Now we won't be doing that. We won't be providing any X values directly. Instead of that, what I'm going to do is I'll have an embedding layer over here. And this will have the X values. So let me give here as X of 1, so X of 2, X of 3, and then we'll have X of 4. And then similarly, let's take this model to be multiple input and single output. So here we'll have y hat of t, and then we'll have weights obviously. So this would be u, v, and w. And this is nothing but our matrix over here. So this would be a of 0, a of 1, a of 2, a of 3, and finally a of 4. Okay, so this is our context matrix. And obviously we'll be performing an activation function here. So I'll just give it f. You can put f, you can put g, it's totally up to you. So this is how a recurrent neural network would actually work. All right. So now that we know how RNN works, let us now understand what is LSTM, or we can also say it as long short-term memory. You see, traditional RNNs are not good at capturing long-range dependencies. What I mean to say here is that when we tend to work with a very huge data set and multiple RNN layer, we are at the risk of vanishing gradient problem. Now you might be wondering, what is this vanishing gradient, right? Well, you see, when training a very deep neural network, gradient or the derivatives decrease exponentially as it propagates down the layer. This is known as vanishing gradient problem. These gradients are actually used to update the weights of a neural network. But when the gradients vanish, these weights will not get updated. In the worst case scenario, it will completely stop the neural network from training. This vanishing gradient problem is a common issue in very deep neural networks. So to overcome this vanishing gradient problem in RNNs, long short-term memory was introduced. You see, LSTM or long short memory is a modification to RNN's hidden layer. LSTM is capable of remembering RNN's weights and their inputs over a very long period of time. In LSTM, in addition to the hidden state, cell state is passed down to the next block. The way LSTM works is that it can capture long-range dependencies, that is all weights. It can have memory of previous inputs for a very extended time duration. The way LSTM cell does this is by using three main gates. First one is a forget gate. Forget gate removes the information that is no longer useful in the cell state. Then we have input gate. Additional information to the cell state is added by input gate. And finally, we have something called as output gate. Additional useful information to the cell state is also added by an output gate. This gating mechanism of LSTM has allowed network to learn the conditions for when to forget, ignore, or keep information in the memory cell. So let me now quickly move to my Jupyter notebook and show you how I can implement LSTM on name entity prediction. Alright, so let me quickly move there. Alright, so over here, first off, I'll be opening my Google Collab. Okay, so let us give a name for our Google Collab over here. Let's give a short term, right? Name entity prediction. And let's connect our Google Collab to our server. Okay, meanwhile that's connecting. So now you might be wondering, from where am I going to use my data set? So for me to use my data set, I'll just go for Kaggle, K-A-G-G-L-E, baby names. So let me just quickly show you how this data set would look like. So this is a CSV file over here. All right, so as you can see here, we have over 93,889 unique values. Okay, so this is a very huge data set. And let's try downloading this. To download this is pretty simple. All you need to do is click this and it will get downloaded. As I've already downloaded this file, let me quickly upload this on my Jupyter notebook. So let me go here and upload it from here. Okay, so let me go to this upload file. And yeah, so I have my CSV file here, and let me open this. As this is a pretty huge data set, it would take some time. Meanwhile, that's loading. Let's see what we can do. So first off, let's import a couple of libraries. So we'll have import pandas as PD, and then we are going to import numpy as np, and then we also need to have matplotlib. So from sklearn. All right, and we also need something like label encoder, but I'll show you a shortcut way to bypass label encoding. Okay, so let's try to load our cell here. And in order for us to read this data, so it's pretty simple. All we are going to do is let's give this as a data. This would be nothing but pandas dot read csv, and then we are going to pass our file name. Let me change this to our root directory. We're putting a dot over here. Okay, so I won't be executing this as of now because it's trying to load our file. All right, so now that we have successfully loaded our data, so let's try running this cell over here. Okay, so let me close this and let me zoom in over here. So now what we are going to do is let's see the shape of our data. So let's see what's the data shape, data.shape, and now let's see what it would be like. Okay, so as you can see here, we have 5 columns, but the number of rows that we have is 1.8 million. That is approximately 18 lakhs, right? So this is a pretty huge value. So now what we're going to do is we'll just see how our data is looking like. So we'll see data.head, and let's see what we need. So as you can see here, we have ID, which is of no use for us. Then we have name. Okay, then this year, I don't think it's of any use for us. Then we have gender and count. Count here represents, how many people have the name Mary, how many people have the name Anna, how many people have the name Emma, Elizabeth, and Minnie. This is over here. Out of this, if you see, right, there are a couple of things that we don't need. We can drop them out. All we need is a name. Okay, and then we also need the gender, because this is going to be our prediction. We are going to predict, we'll give our own custom name, and then we'll see whether the name that is we are giving is a male or a female. Okay, so now what we're going to do is let's see how many unique values we have. So let me quickly erase this first. Okay, so what I'm going to do is data.names. So this should give us here name, and then we'll type here as unique. Okay, so this would give me unique values. Okay, so over here I have 93,889 unique names. Okay, so now what we're going to do is we want to label encode this, right? So we want our female, which is nothing but F, we want female to be 0 and then male to be 1, or vice versa. So in order to do that, either we can use label encoder, or there's a shortcut method to this. Let me quickly show you how that works. So first off, we'll take our data frame. So it's data, and which column we want to do this for? We want to do this for our gender column, right? So let me pass this and give gender. And now what we're going to do is, okay, we'll take this as type. Okay, this would be obviously in the form of category. And now what we'll do is this is cat dot codes. Okay, so this is nothing but panda shortcut, do label encoding. Let's try to execute this and see what it would look like. So as you can see here, we have a couple of zeros and ones. This is nothing but it's representing females with 1 and males with zeros. Okay, so now what we'll do is we have to update this column. So we'll paste this, and this should be something like this over here. And let me execute this. Okay, so if you want to see how our data would look like now, let me just quickly run this once again. So you'll see here now the values has been label encoded. Okay, so now what we're going to do is we obviously need to take the unique names, right? And then we'll obviously group it by, right? So what we'll do for this is we'll take something like data. We'll group this by the names. So group by names. All right. And now what we'll do is we'll calculate the mean of the genders. We'll reset the index. The reason why we want to reset the index is because, if we don't give the index, then our name over here will become the index, right? So we'll give reset underscore index. All right. So let's give this to a new data frame, and we'll call this as df. Okay, let me execute this now. And let's see how this df would look like. Okay, let me execute this right after this. So as you can see here, it has grouped by names, everything in an ascending order. So this is all in an alphabetical manner. And yeah. And now only thing that I want to work on is this gender. Okay. The reason is because over here I'm getting a floating point value. I don't want this floating point value. I want to change this to integer value, right? So what I'll do is df gender. This would be nothing but df gender. Then all I'm going to do is as type. I'll just put here as int. So let's now see what this value would look like. Fantastic. We over here have now, ones and zeros, which is nothing but an integer value. Okay. So if you want to see this, so either I can write df or I can also put as head. Okay. So these are the first 5 values. Okay. So now the way our neural network is going to work, or the recurrent neural network is going to work, is that, I hope you remember these boxes, right? So when I was talking, or when I was explaining this RNN, I was saying that I would be passing around the words. But here in this project or in this program, we won't be passing words over here. We won't be passing like Abha or Abida or Adam. We won't be passing these words. Instead of that, we'll be passing letters. So over here, it's going to be like alphabets. So A, B, it can be any alphabet, it can be Z here. So basically it depends upon whatever the value is coming here. So in order to do that, we have to find number of unique alphabets. So we know how many unique alphabets we have, right? So it's 26. So in order to get these alphabets, what we'll do is, let me first quickly erase this. Erase all drawing. So now we have 26 alphabets. We have to create our own vocabulary. So what I'm going to do is I'm going to import string. So now I need letters, right? So letters, this would be nothing but list of string.ascii. Okay. And if you want to see what this would give me, this would be nothing but the list of alphabets, which are in lower cases. Okay. And now what we'll do is we'll try to create a label encoding, or we have to create a vocabulary, right? So we'll have something like vocab. This would be nothing but I'll be using dictionary. And now what I want is zip. The way I want over here is, for every individual values of this A, B, C, D, I want to label encode this to 0, 1, and whatever the value it is, right? So it would be from 1 to 27, unique numbers, right? So this would be nothing but letters. And then we need something like range 1, 27. So this would give me the matrix from 1 to 26, right? And let's now see what this would look like. So we have vocab, and let me execute this. This should give me a dictionary. Okay. So here we'll convert A to 1. Okay. And then B would be 2, C would be 3, and so on. Z would be 26. And now what we are going to do is we'll just try to create the reverse vocabulary. And the reason is we obviously won't be needing this, but just in case if you want to use, it should be something very similar to this. Let me just copy the exact same thing and paste it over here. So we'll just give it as reverse, right? So it will be R underscore, and here instead of numbers being second, we'll just cut this letters and we'll pass letters over here. And now you'll see if you're trying to decode whatever we have predicted, we can just pass it down like this. Okay, so now what will happen is we need to do something like, all our data, whatever is there, we have to convert them into a lowercase. So, and then once we convert them into a lowercase, we have to encode them into numbers. So whatever I'm saying is this AABAN, right? ABAN. So this AA, obviously first of all, we have to convert all of this into a lowercase, this value. And then whatever the equivalent value of A, the numerical value of A, so it's obviously going to be 1. We'll substitute that with this, and it's going to be a list, right? So how do I do that? So for that, I'll write a function. So we'll have def word to number, right? Word to. So now what I'm going to do is I'm going to have for loop for I in range. So this would be nothing but we have to go through the entire shape, right? So df dot shape. This would give me a list, and I just need the first index. Okay. So now what I'm going to do is I'll create one new list sequence. This would be nothing but for letters in df. Obviously we want the names part, and in this we are going to pass the index value. It's going to be I. Let me just give some space here just so that you better understand this. And now what I'm going to do is, I'll have this vocabulary, vocab. See, every time I pass a letter, it will convert it into, this individual letter, it will convert it into a list or the equivalent, numerical representation. It will be letters, and obviously it has to be in lower, so it will be lower. And then we'll just close this bracket here. So now what we are going to do is, before we execute this function, we'll have to append this. So it will be df, and this is going to be names dot I. We'll replace the name in that index with this particular sequence. Okay, so now all we need to do is run this function over here, and yeah, this will take some time. The reason is because we have almost around 18 lakh values. So yeah, this will take some time. Meanwhile, let me just comment this. Okay, so in the next stage, what we are going to do is, let's see how our this value over here would look like. So let us now first execute this. All right, so let us now see how our data frame will look like. So let me execute this block now. So as you can see here, our names have been completely changed or converted into a list of numbers. But now only issue that we are trying to have is the imbalance in the size of the list. Because when we are trying to have the number of boxes, right, we won't be having variable number of boxes. Okay, so what we're going to do is either we set a value like something like take an average number like 10, 20, or you can take something like, something like you either depend on maximum number or the minimum number of list. But the thing is, if you take the maximum number, then we have to pad a lot of zeros, and this would lead to a loss. So if I reduce the size, this would also decrease the accuracy, right? So what we're going to do is we'll plot this name and gender in the form of a histogram. So let's take here X. This would be df names, and we'll give here as dot values. And then same thing, we'll do it for Y, df gender, and this would be dot values. So what we'll do is we also need a list. Okay, so now as we are going to plot this on a histogram, and what we are going to see in the histogram is just to analyze, this is a graph. We want to analyze, where does the highest number of sequence, or if suppose this is a size, if this is size 8 and this is like 8,000 words or 8,000 names have the size 8, then we can keep our average somewhere near, and then we can also decide, if the number after 10, if not many names have a longer number or the longer length of that name, so we can keep our average somewhere around 9 or 10. Okay, so let's now quickly see how we can do that to get the length of our names. So length X or name length, this would be like list comprehension for I in range 0, df dot shape of 0. And now what we're going to do is we need to find the length. So this would be length X of I. Over here you can either give df or you can also give this X, right? So it would be length of X. Okay, so let me quickly execute this. Okay, so here we're getting an error. Oh yeah, it's not O, it's going to be 0, right? So let me execute this now. Okay, so let me show you how this would look like. Name length, and let me print this off. So as you can see, this is giving me a list of names. So there are a huge amount of names. So as you can see, first we had 5, 5, and then 9. So let's now plot this and see how it would look like. Import matplotlib splt. All right, this is perfect. So now what I'm going to do is I have to plot this, right? So all I'm going to do is plt.hist. All right, and now I'm just going to give name length and number of bins. This would be like, let's give 20, okay? And then plt.show. Okay, so what do we find from this graph over here? You see, this is nothing but the length of the names. So 2, 4, 6, 8, 12, all these are the length of the names. And this is nothing but 0, 5,000, 10,000. This is nothing but number of names that have a length 4 or number of names that have the length 6. So as you can see, right, there are around almost 25,000 names whose length is 6. And then as I cross like 10 or as I cross 12, not many names are there whose length is greater than, 12. So what I'm going to do here now is, now we have to pad, right? Now we have to pad the number of zeros. So in order to pad zeros, we have something called as built-in function from Keras. So from Keras, or you can also set as Keras dot preprocessing dot sequence import pad sequence. So let me quickly execute this now. And now what I'm going to do is I'm going to create a new list. So let this be X. This is in lowercase. So pad sequence. And the things that this is going to take is obviously the sequence. We have to give a list of sequence. Okay. And then we'll give something like df.names. And then this is going to be values. And now we want to define the max length. So this is going to be 10. We also have an option of providing where do you want to do the padding. So you can also do it as pre or post. We'll obviously be doing pre. So let's see, how do we do that? this should be nothing but, if you can see this sequence over here, so we have padding is equal to pre. It's by default, right? So pre. So let me execute this now, and let's see how this X would look like. Okay, so as you can see here, X is a matrix whose length is 10. Okay, so each of these, like this is nothing but 19 million cross 10. So there are 10 columns throughout all. So now what we're going to do is we're going to create our own model. So for that we'll do from keras.layers import input layer, and then we have to have embedding layer, because if you don't have embedding layer, then it would be like each input would be something like 1.9 million, that is 18 lakhs. So it's a pretty huge value to compute, so we don't want that. So that's why we'll use embedding layer. Then we have dense layer, and then we have LSTM. We also, rather than taking this as a sequential model, we'll take it as feed forward. So what we'll do is from keras.models import model. So now what we are going to do is we'll have to create our input layer. So this will be input is equal to input. And now the shape that we are going to pass over here. So for this shape, so how many columns do we have? We obviously have 10 columns, right? So it's going to be 10. So now what we're going to do is next we are going to have embedding layer. So let's say this is EMB and this would be embedding. So input over here, or the input dimension over here, is nothing but vocab size. We haven't defined this vocab size, so let's quickly do that. So vocab size, this would be nothing but length of vocabularies plus 1. The reason why I'm doing plus 1 is because we also have zeros over here, right? And this would be like vocab size if you want to see. And let me execute this. So we have 27, right? So 26 are the number of alphabets, and 1 is because we have number of zeros. So we'll pass this as vocab size. Okay, and now we are also going to pass output dimension. So output dimension, this is nothing but how many dimensions we want. So now this is going to be 5. All right, and the input for this embedded layer is going to be from INT. Okay, and now we are going to have our first LSTM layer. So it's going to be LSTM1. So this will be LSTM layer. Number of units we have to define here. So units, this is going to be like 32. The units over here does not represent the number of boxes. The units over here represent the A values, right? So now we have to do return sequence, and this is going to be true. And the input for this is going to be from embedded layer. Then we have LSTM second layer, and this is be LSTM units we're going to pass. So number of units that we're going to pass now is 64. And now the input for this is going to be LSTM1. Finally, we have an output layer. So at the end, right, we're going to have a dense layer, right? So dense. So number of units or number of neurons at the end, we are going to have 1. And kind of activation function that I'm going to have here is going to be sigmoid, because we have to predict either it's a male or a female. Okay, so sigmoid, and the input for this is going to be LSTM2. So finally, we have to add this to our model. So I'll give it as my model. This would be model. So now I have to define the inputs. So inputs, this is going to be inputs, inp, and outputs, this is going to be out. Okay, so let me quickly execute this now. Okay, so we have this error. Please provide either a shape. Okay, so let's see what's, oh yeah, here I've given it as sparse, right? So it's not going to be sparse, it's going to be shape. So let me quickly execute this once again. Okay, as you can see, we have successfully executed this. And now let's see the model.summary. So as you can see here, first off, we have input layer. Okay, so we can have a number of values, but there will be only 10 features. Okay, that's 10 columns. And then we are going to have, once you go through this embedding layer, then instead of having 10, instead of having that 1 million or whatever it is, 1.8 million, we'll have just 135 parameters. Okay, similarly over here, and finally at the dense we have 65 parameters, and then we have 1. The reason why we have 65 here, just for if you don't know, is because 64 plus 1 bias, and this would give us 65. Okay, so now finally we are going to train our model, but before that we have to compile it. It's going to be my model dot compile. Okay, so we have to find an optimizer. So optimizer, best one that I feel is Adam. Then we have to find the loss. So as we are going to use just 2 predictions, right? Either it's male or female, we'll use binary cross entropy. And then finally the matrix that we want to use here is, this will be accuracy. So let me execute this now. And finally we are going to compile this. So we'll have history. So this will be model.fit. Okay, and now we're going to pass our values. We're going to give x, we're going to give y. As you know, x is nothing but the matrix which has a padding, and y is nothing but the other classes. They're telling us either it's ones or zeros. And number of epochs, this is going to be 10. Batch size, as it's a pretty huge data set, we're going to keep a pretty high batch size. So I'll give a batch size here as 256. And then finally we need validation split. Okay, it's not going to be my model, it's going to be my model, right? So my underscore model. So finally we're going to have validation split here. So let's give it as 20%. So it's going to be 0.2. All right, so finally it's the moment of truth. Let us now execute our code. This would take some time to execute. So let's see how this would look like. Okay, so if you can analyze this data over here, so as you can see, right, this validation accuracy has to increase. And we cannot see every time, if our model is overfitting, the accuracy over here will keep on increasing. All right. So the more reliable source over here to see is nothing but validation accuracy. So if validation accuracy is increasing, that means our model is neither overfitting nor underfitting. And you can also see that we have our validation loss, which is kind of decreasing. And over here as well, we can see the validation loss. Over here, we can see the loss of a model is decreasing from 60, then 40, then 39, 39, and 80, 38. So let's now wait for a few more epochs. So we have 4 more to go. Okay, so as you can see here, our validation accuracy has been increasing. So this is a very healthy growth. And even over here, our accuracy of a model is also increasing. Fine. And the loss is decreasing. It's decreased from 60% to 37%. And over here, our validation loss decreased from 42% to 36%. So let us now map this, like whatever values we have received. So in order to map this, we have h. This model over here retrieves us the history function, right? So we'll give hist.history, and let me execute this. Okay, so now what we're going to do is, this is nothing but key value paste. So if I put h, if I give something like accuracy, okay, well, let's plot this. So model.plot, right? So plt.plot. Okay, we'll have accuracy. We'll compare this with respect to accuracy, and then plt.plot. Then we'll have validation accuracy, and we want to show this, right? So plt.show. So as you can see here, okay, so just to give a better analogy, let's execute one of these first. Okay, so the blue line over here represents the accuracy of a model, and then this is nothing but the accuracy of our training data, right, or testing data. So as you can see, our model accuracy isn't decreasing, so it's a very good model and it has trained very well. So now coming down to the moment of truth. So let's now take a random name and see whether it can predict whether the name is true or false. Okay, so we'll give here as test_name. So let's give something like, this will be like name, right? So we'll give name.lower. And now we are going to pass the name over here. So this would be, let's say, Tom. Okay, so we have to convert this into letters, right? So it will be vocab of I for I in test name. And now we'll give the name here as xtest. So this would be nothing but we have to pad the sequence, pad sequence. We'll pass this in a form of a tuple. Then this would be seq. And then we know that we have to pad 10, right? And anyways, we don't have to say whether it's pre or post, because by default it's going to be pre. Fine. So let us now see how our text data would look like. So x test string attribute has, okay. Oh yeah, so I have done a typo over here. It's going to be LOWER. So let me execute this once again. So as you can see here, we have a matrix which has a size of 10. And let's now see what this would predict. So it's the moment of truth. So y.predict, this would be model.predict, and I'm going to pass here as xtest. And let's see what does this predict. So we'll give here as ypred, and yeah, let us execute this. Okay, so we are getting this in a form of an array. So what this tells us, this tells us that, this is like 70% chances that this name is Tom. In order to make this, layman stuff, so what we are going to do is we'll have if ypred. Let me execute this first. So let me go down to another block. So this would be something like if ypred is less than 0.5, then we'll say the name is female, okay? Else print name is masculine or name is, or let it be male, okay? So same thing over here, we'll just keep it as male. So let's now see what this thing predicts. Okay, so this thing predicts male. So let's take another common name. Let's take something like, let's go to Google and see what name can we take. Yeah, we can take up something like Brad Pitt. Okay, so let's execute this and let's execute this again and then this. So as you can see here, this is giving me a male name. And let's give a female name over here. Let's give as Mary. And let's see whether this would predict it as male or female. So as you can see here, it's female. Now, as if you have seen the data set, right, it says this is the name from the US kids, right? What will happen if I give an Indian based name? So let me give an Indian based name like Priyanka. And let me execute this. It's giving me a female name, right? So this is something pretty astonishing, right? So why do you think it gave me a female name? Well, the reason is because when we are training this model, like RNN, using RNN, right? It's not looking at the name. It doesn't know whether the name is female or not. But as a matter of fact, it is looking at the pattern. Okay, so it might be looking at, if the name ends with so and so, it is a female. If the name starts with this, or if a name have something like this, it means, it's a female or a male. So to give you a better analogy, let's give something like Julia. So let me execute this. This will give me a female, right? So what if I give something like Junaid? This would give it as male. So all it's trying to do is it's trying to see, recognize a pattern. That's why it's taking individual words at the same time. So this is what makes NLP using LSTM very effective. All right, so moving ahead, let's see some of the LSTM's use cases. You see, LSTM is a very popular deep learning algorithm for sequential models. Apple Siri and Google's voice search are some of the real-world examples that have used LSTM. And you won't believe it, LSTM is a success story for those algorithms. So let us now have a look and see how LSTM changed that technology. Okay, so starting off with Apple. In 2003, Apple was the first major tech company to integrate a smart assistant, that is Siri, into an operating system. And the Siri was actually a byproduct of some other company. So Siri was a company's adoption of a standalone app that has been purchased along with the creators who made it. It was somewhere in 2010. The initial reviews about Siri was that it was intense. But over the next few months and years, the users became more impatient with the shortcomings. And all too often, it wrongly interpreted commands. And then, no matter what you do, there was no fix for it. So this is when Apple moved Siri's voice recognition to a neural-based system. Some of the previous techniques remain operational, something like, applying hidden Markov models. But most of the time, DNN or deep neural network using LSTM was used. Although people did not find any changes on the outside, but from within, it was a supercharged deep learning model. Speaking about Google's implementation, Google implemented Google Voice Search somewhere in 2009. Google Voice Transcription had initially used something called as Gaussian matrix model. This was nothing but an acoustic model, and this was something considered to be a state-of-the-art speech recognition for almost 30 plus years. But it was in 2012, there was a boom in deep neural network. And when Google implemented deep neural network, that too using multiple layer networks, there was a huge performance gap. But things really improved when the Recurrent Neural Network, especially with LSTM RNN, first launched on an Android speech recognition in May 2012. Compared to deep neural network, LSTM RNNs have additional recurrent connections and memory cell that allows them to remember the previous data. Alright, so moving ahead to our last topic of our session, let us now see some of the real-world applications of LSTM RNN networks. First off, we can perform name entity recognition. This is something which we did in our previous demo, right? So what is this name entity recognition? You see, name entity recognition is a subtask of information extraction that seeks to locate and classifies name entity mentioned in an unstructured data. Okay. Next, we have something called as sentiment analysis. Sentiment analysis is a predictive modeling task where model is trained to predict the polarity of a textual data or sentiments like positive, neutral, or negative. Sentiment analysis is performed by various businesses to understand their consumers' behavior towards the product. Then we have machine translation. The task of machine translation consists of reading text in one language and generating text in another language. When neural networks are used for this task, we talk about neural machine translation. Within neural machine translation, an encoder-decoder structure is quite a popular LSTM RNN architecture. Alright guys, with this we come to the end of our session. I hope you enjoyed and learned something new. If you have any further queries, please do mention them in the comment box below. Until next time, goodbye and take care.